In the previous video, we had discussed about the dual nature of matter and in its in-text questions. So dual nature of matter is applicable to microscopic particles. Similarly, there was another concept called as Heisenberg's uncertainty principle, which was given by Werner Heisenberg, who was a German physicist in the year 1927. According to this principle, it is impossible to determine simultaneously the exact position and the exact momentum of an electron. So imagine as we know from Bohr's model, he said that electrons go in circular paths or orbits. So according to Heisenberg's uncertainty principle, we cannot figure out both electrons' velocity as well as its position at the same time. Okay, so mathematically speaking, you have delta x into delta p is greater than or equal to h by 4 pi, where delta x is the uncertainty in position, whereas, sorry, this is supposed to be uncertainty in momentum, and delta p is the uncertainty in momentum. So as we know, so the reason you have the greater than and equal to sign over here, it means that the product of uncertainty in position as well as momentum should always be greater than or equal to 4 pi. So it can never, this value can never be less than h by 4 pi. And okay, so if x delta x is small, okay, position of the particle will be known. So we know the position of the particle, then the uncertainty in the position in the momentum will be large. Similarly, if delta p is known, that is the momentum is known, then the value of delta x will be very large, or rather the uncertainty in position will be very large. Okay, so momentum of a particle, that is P, equals to mv. Like I said, this is supposed to be momentum. So this is not position. Okay, so P equals to mv. That is, the momentum is equals to mass into velocity. So delta x, that is the uncertainty in position, into the mass of delta v, which is the velocity, will be greater than or equal to h by 4 pi. And that's why delta x into delta v is greater than or equal to h by 4 pi into m. Now over here, remember, here we are substituting the value of the momentum as mv, m delta v. M cannot change, right? Mass, no matter where that object is, as we learned, it will not change. But velocity can. So delta x into delta v is greater than or equal to h by 4 pi m. Here, delta v will be the uncertainty in velocity. So that is why, according to the Heisenberg's uncertainty principle, it is impossible to determine simultaneously the exact position and momentum or velocity of an electron. Okay, so mathematically, the uncertainty in position into the uncertainty in the momentum is greater than or equal to h by 4 pi. Now, one second. So why this happens is, suppose you have to look at something and you're in a dark room. Okay, the moment you shine light on it, you will be able to view that particular object. So these objects do not take in the energy of the light that hits on them and change its condition. However, electrons, on the other hand, are very small. So what happens is, when you assume, let's assume this electron has this particular path, okay, and when incident photons hit the electron, it will absorb the energy from the photon. All of this is what we learned in, if you think about it, photoelectric effect. The whole concept of photoelectric effect was the absorption of energy by the electron, and that Basically, you had the binding energy, which removed the electron from the metal, and the remaining was used up for kinetic energy, which changed the speed at which the electron gets ejected out. So, when it absorbs the energy from the incident photon, it will get, it will basically move to a newer path. So you don't have like, okay, so you don't know what was its expected path and what, so you cannot determine both the position as well as the the velocity or the momentum of the electron. If you try and measure one, the other one's value will obviously change. So there are two main significances of Heisenberg's uncertainty principle. First, it rules out the existence of definite paths or trajectories of electrons and other similar particles. So first of all, you can say that a particular object has a particular path if you can see its velocity as well as location in various moments. But according to Heisenberg's uncertainty principle, we cannot determine where the particular object is and what its velocity is at the same time. So we can only tell if where it is or where it was a few minutes earlier or later. So we cannot just say uh, the position of the object is at so and so place and fix its trajectory. So we cannot determine both of these simultaneously. So since you have subatomic particles are very, very small, it is very difficult for us to determine both an electron's position and velocity. And so I mean, like you can't say that it's a particular value as such. So there will not be, I mean, you will not get an exact value. And because of that, we cannot say or talk about the trajectories of electrons and other particles, other similar particles as in the small particles. The second significance is the effect of Heisenberg's uncertainty principle is significant only for the motion of microscopic objects and is negligible for that of macroscopic objects. So something similar to this is what we did for dual nature of um, de Broglie's dual nature of matter. So according to that, we had compared the wave nature of both a microscopic object and a macroscopic object. So for a microscopic object, the wave nature is very pronounced, whereas for a macroscopic object, it wasn't. So when Heisenberg's equation is applied to an object whose mass is 1 milligram, then you'll have delta V into delta X equals to h by 4 pi. And that's equal to, this is the Planck's constant, so 6.66 into 10 to the power minus 34 joules second, and 4 into 3.1416, that is the value of pi, into 10 to the power minus 6 kilograms. Since we took milligrams, we just converting it to kilograms so that it's easier for us to cancel the units. Okay, so in the end, you get 10 to the power minus 28 meters minus 2 second minus 1. So this means that the uncertainty is very, 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 very less. So delta V into delta X, that is the uncertainty in the velocity and the position, is very less. However, when we apply it for an electron whose mass is 9.11 into 10 to the power minus 31 kilograms, then the uncertainty in position and the velocity is 10 to the power minus 4 meters to the power minus 2 and second to the power minus 1. So if you notice, the 10 to the power minus 4 is obviously higher than 10 to the power minus 28, which means there is a huge, or rather there is a lot of uncertainty in the product of these two values. Now, let's assume that we know the position or the location of the electron and it has the uncertainty is 10 to the power minus 8 meters. So when we substitute that, we can figure out that the uncertainty in velocity is 10 to the power minus 4, which is also high. See, compared to this 10 to the power minus 8, 10 to the power minus 4 is relatively high. So this means that when one of the value is known, the uncertainty in the other value is extremely high. That is the basic idea behind Heisenberg's uncertainty principle. So basically, we cannot figure out the momentum or the velocity as well as the position of the electron at the same time. I'm not saying you cannot figure it out, but we cannot figure out both these values at the same time. Now, there are various reasons. I think we spoke about the various reasons for the failure of Bohr's model. There we specifically told the last point in that was about the Heisenberg's uncertainty principle and dual nature of matter. There are 4 or 5 other points apart from this, but I just wanted to go over it once more. So the electron, according to Bohr's model, is considered a particle which goes around the nucleus in a proper circular path. But the wave character is not considered. So dual nature of matter basically believes in the wave character of wave and particle nature of a particular subatomic particle, that is an electron in this case. So the wave character is not being considered, and an orbit is a defined path. But according to Heisenberg's uncertainty principle, we cannot figure out the exact position as well as the momentum. And if we can't figure out these two values, we cannot talk about the exact position of the electron or the exact path of the electron. We can only predict its presence. So it does not. So Bohr's model ignores the dual behavior of matter as well as contradicts the Heisenberg's uncertainty principle. So the atomic model considers the dual nature of particles as well as the Heisenberg's uncertainty principle was required, and that is where the quantum mechanical model came in. So these are the various reasons for the failure of Bohr's model. There were few others, but here I'm focusing on the last point of that particular video where we spoke about dual nature of matter and Heisenberg's uncertainty principle. So in this video, we learned about the Heisenberg's uncertainty principle, the mathematical equation and its explanation, significance of the Heisenberg's uncertainty principle, and the reasons for the failure of Bohr's model. So in the next video, we will be solving a few in-text questions related to Heisenberg's uncertainty principle. But after that, we will start with the quantum mechanical model, which basically gave a solution to all these new concepts that had come up.